Morning, everyone. We've been talking a lot about ionic and molecular compounds, and now today what we're going to talk about is how to represent those ionic and molecular compounds in a actual reaction. So this is the getting into these skills that most chemists and all chemists use to communicate information about a specific reaction, about the reactants and the products that are formed. So this lesson is going to be on word and skeleton, and then I'll release another video on balancing equations. Kind of the main idea here, kind of the main idea here is that there are three ways that we can represent reactions. One of those is through word equations, one of those is through skeleton equations, and the last one, which we won't get to in this video, will be balanced equations. And so with word equations, sometimes a chemist uses a word equation. A word equation is one way of representing a chemical reaction. Generally speaking, how they appear, let's get actually into this PowerPoint here. Generally speaking, how they appear is like the following. They'll have their reactants on the left, and it turns into the products, like such. And so the reactants usually will be separated. While it might be separated by, let's say, a plus sign, that'll tell me that there are two different reactants and those are turning into this one product. So the arrow kind of acts as like our equal sign. Some of the terminology that gets used for this arrow would be like it yields this product, it forms this product, it produces or reacts to produce or decomposes into. Reactants are all the stuff that we start with, and they always exist on the left side. Products are the stuff that we end with, and those always exist on the right side of the arrow. So that's the general format for all of our reactions. So, for example, if we placed hot steel wool, which is made of iron, into a bottle of oxygen, we would have iron 3 oxide being created. So, that right there, this is like a word problem, kind of similar to math, where now we have to take that information and translate it into actual chemical information that we can represent. And so we do so by saying that we had iron originally in the form of the steel wool, we had oxygen, which was in the bottle, and that turns into iron 3 oxide. And this isn't, this would be a word equation. So this would be that first method of the three. Most chemists will not use this. They'll use skeleton and then extend that further into a balanced chemical equation. But that's what a word equation would look like. And so another example would be carbon dioxide and water produced during human cell respiration. The reactants are sugar and an important gas that humans need to survive, oxygen. The word equation for this reaction would be sugar and oxygen goes to form carbon dioxide and water. And right now, I wouldn't expect you to know that these are the two products. We will eventually get into types of chemical reactions, and then you'll be able to predict the products just solely based on the reactants that you have. So that's word equations. They're slightly useful. Skeleton equations are immensely more useful. And so what they do is they say, okay, great, we know that we have both iron and oxygen forming iron 3 oxide. Let's just translate all of those into the chemical formulas. So that's why we've been grinding out so hard the molecular and ionic compounds over the last couple of weeks so that we can then translate this information now into changing these skeleton equations or these word equations into skeleton equations and then eventually into balanced chemical equations. So that right there is the balanced chemical equation. We'll learn about oxygen in a sec, but oxygen is something called a diatomic element, meaning that when it's by itself, it's incredibly unstable. And so whenever you find oxygen in the atmosphere, it will always be O2. In other words, there will be two oxygen atoms that will be linked together. Kind of looks like a guy's eyes or a pair of glasses at the bottom here, but they will always be found together in the atmosphere. So whenever you're reacting with oxygen, you're breathing in O2, not pure oxygen. Iron just being Fe, it doesn't have a charge at all because it's by itself. That's another thing that's kind of worth noting here. These guys do have charges on them. So iron does have a charge, and because it's iron 3 over on this side, we would know that this would be Fe3 plus, and we know that this would be O2 minus. Because these elements are by themselves, they don't ever have a charge. So you can think of it this way. You can have lead in your pencil, and that lead can exist in your pencil. It does not have a charge when it's in your pencil. It's just lead. Similarly, you can have hydrogen gas. It's just hydrogen gas. It does not have a positive or a negative charge. It's just hydrogen gas. So you can have elements in their pure state. where they do not have a charge, they're not reacting with anything. And that is when they're by themselves like this. We would call those pure elements. If you remember the flow chart that we did, these guys would act as pure elements. And then when they react to form an actual compound like such, when they react to form a compound, that's when we need to be concerned about their charges. So Fe3 plus and O2 minus. And that's when we need to swap and drop. Or if it's a molecular compound, that's when we need to use our Greek prefixes to decide how many of each element there will be. The other example that we looked at, again, there's no way I would expect you to know this, but this is one of the key reactions that we eventually talk about in Bio 30, where we have sugar and oxygen going to form carbon dioxide and water. Again, oxygen's diatomic, so when it's by itself, there's two of them. And that leads into this conversation here about diatomic molecules. So again, these elements, all of the metals for sure, they can exist by themselves as just pure elements. And they do not have a charge. They do not need a buddy. They're stable by themselves. We're going to talk about the 7 of 7 rule really quickly here. There's two different ways that you can remember this. One of them is you can remember Hoff, Brinkle, like such. You can remember Hoff, Brinkle. I personally remember the 7 of 7 rule. So the 7 of 7 rule is you start at element number 7, which is nitrogen, and from that you draw a 7. And that would be the 7 diatomic elements. So you would know it would be nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. If you're counting, you notice that there's only 6. So the weird one about the 7 of 7 rule is that we neglect this hydrogen. Hydrogen is also a diatomic element. So you can remember Hofbrinkel, Hof, HOFBRINCL. You can remember Hofbrinkel, or you can remember the 7 of 7 rule. Either one is fine. And again, what that is showing us is that is showing us the diatomic elements. So those elements are always written with the subscript 2 in skeleton equations, but only when they're on their own. So for example, like if we had H2O, we do not need to put a 2 beside this oxygen here. It is not by itself. It's only when those elements are by themselves that they get the little 2 beside them. And again, that's just because they're very unstable elements that need a buddy. They usually exist as gases, so they need a buddy so that they're not just constantly reacting with everything. It keeps our universe stable and in control. So for example, we have example here at the bottom when nitrogen and oxygen react to form NO2, which would be nitrous oxide, or nitrogen dioxide. Again, this is nonmetal and a nonmetal, so we know it's a molecular compound. And we would know that there's one nitrogen. We don't want to say mononitrogen because it's the first element listed. So nitrogen dioxide. And then we have these two diatomic elements reacting to form it there. And so that's it for the first skeleton equation. Little lesson here. We will then transition into talking about balanced chemical equations in the next video. Have a good rest of your day.